Good morning, students. Welcome back to online class section of Analog Communication. This is Aisha Sultana, Assistant Professor of ISL Engineering College from ECE Department. So in today's class we are going to discuss about single sideband suppressed carrier modulation, okay, or single sideband modulation. So here in this way, before going to start in this video, first quickly revise what was the last topic we have discussed in the class. I hope everyone remember that one. That was your Hilbert transform, yes or no? So Hilbert transform, what was Hilbert transform? Hilbert transform, like of other transforms like Fourier transform or Laplace transform, we are not going to change the complete domain of your signal, that is from time domain to frequency domain or from frequency domain to time domain. We are not going to change the domain will be same as of your time domain, but only the phase shift will be changed. Your signal will be in time domain only, but phase shift will be done depending upon your frequencies, either positive or negative, and the phase shift will be of 90 degrees, that too plus or minus 90 degrees. In case if you are having positive frequencies, then you will be having minus 90 degrees of phase shift. If you are having negative frequency components, then you will be going for positive or plus 90 degrees of phase shift. Okay, this Hilbert transform is mainly used in your modulation process. So in a single sideband or a double sideband, you will be using this Hilbert transform. So that's the reason this Hilbert transform has been introduced in your analog communication. Okay, so today's topic is about your single sideband suppressed carrier. By listening the name itself, you know what actually we are going to do in this one, isn't it or not? So what were the disadvantages of your double sideband suppressed carrier? So we quickly revise from the starting. Conventional amplitude modulation or double sideband full carrier signal, correct? So what was your normal amplitude modulation? Your modulation means superimposing of your message signal, carrier signal onto the message signal. Now what is meant by amplitude modulation? The amplitude of your carrier wave should be changed, or it should be varying in terms of amplitude, that too with respect to your message signal, right? So there we had two disadvantages. One was we are having a carrier wave which is consuming 90% of the power, but all the information or data which is present only in sidebands. So as to reduce that disadvantage, what we have done, we have suppressed your carrier by using your double sideband suppressed carrier. There you have suppressed the carriers. Now only sidebands we are transmitting by using your SSB-SC. But SSB-SC also got two disadvantages. The very first disadvantage is that we are wasting the channel bandwidth in other resources, because the two sidebands, that is your upper sideband as well as your lower sidebands, they both are having identical or same information. So why we have to waste two sidebands? Why we are wasting the bandwidth in why we are sending two sidebands at a time and wasting the bandwidth? So as to reduce that one, we are suppressing a single band. Means we are only passing only one sideband and suppressing one band. Okay, only either upper sideband, either lower sideband will be transmitted from the transmitter to the receiver. That is the first disadvantage of SSB-SC that will be overcome by your SSD. Secondly, you are having, that is your complicated, your system will be complicated. Why? Means in SSB-SC what we have said, we are suppressing the carrier. Here also carrier is suppressed. Already carrier is suppressed, so only sideband will be there. Here also the complexity will be increased, because you are suppressing the carrier. At the receiver side also we have to get a carrier by using a local oscillator, and synchronization should be proper when you are getting that when you are getting that signal, modulated signal. Okay, so here also complexity will be remaining, but the first disadvantage of SSB-SC will be reduced by using your SSB, that is single sideband suppressed carrier. Okay, only one sideband will be suppressed, only one sideband will be passed to the carrier, so that the bandwidth will also be reduced and the power consumption will also be reduced. So this is the advantage of your single sideband. And this is you might be having a doubt, what about the second disadvantage? That also be removed, but in next topics. Okay, so first we will define the single sideband suppressed carrier. What is meant by single sideband? So the modulation, single sideband modulation, or the modulation process in which the modulated signal contains no carrier component and has only one sideband. Either it may be your upper sideband or it may be a lower sideband. That kind of modulation is called as your single sideband modulation. Okay, the process or the modulation process in which the modulated signal, what you are giving the signal to the receiver, that signal is having only one sideband, either upper or lower depending upon the receiver, and no carrier component is having, then that kind of modulation process is called as your single sideband modulation. So here I have given the frequency domain representation of your single sideband. So this was your actually AM signal. Here in SSB-SC you are suppressed the carrier. Now I am having the lower sidebands, upper side. These are the two sidebands have separated. Okay, these are the upper side. Whatever the outer portion of the wave, that will be always your upper sideband, and the inner portion of the message signal is called as your lower sideband. So this is how, this is your lower sideband, ma'am, and this is your upper sideband. Either you can pass this. Okay, this modulated signal can be passed through the channel if the receiver wants this kind of signals. Either you can pass this kind of message signal, means lower sideband signal, depending upon the application or the receiver, which kind of application you are using, or what is the frequency or bandwidth that you are used. Depending upon that, only one sideband can be passed. Clear? So the main important thing that we are going to do is you are removing one of the sideband. So the SSB-SC spectrum contains both upper sideband as well as the lower sideband, which are having the same information. So SSB, what you are doing, it is solving the first disadvantage, that it is removing the one of the sideband by using a high pass filter or the low pass filter. It depends completely on the receiver. Okay, and it is filtering out, and then then it is given to the receiver. Means at the what we are saying, it will be filtered out before the transmission itself. Transmission and transmitter is different. At the transmitter side, by using a high pass or the depending upon the filter, we are removing the sideband. Then afterwards it is transmitted, means before transmission, before it is going to the channel, then only you have to filter out one of the sideband. So very important. Now how you have to generate SSB signal? What are the steps to generate your single sideband suppressed carrier? What are the things that you are going to generate? Okay, there are two steps, ma. As we know, we have to filter out, first we have filter out the carrier from the amplitude modulated wave, that is your SSB-SC. From SSB-SC you have to filter out one of the sideband. So for to get that one, what we have to get? First we have to get your double sideband suppressed carrier signal. So first, as to generate your single sideband signal, first you have to generate your SSB-SC. Now that SSB-SC signal should be passed only one sideband to suppress the other. So we are using a band pass filter which suppresses the one sideband and gives only another sideband to the channel. Okay, for generation of this SSB sideband signal, there should be an energy gap between your message spectrum. This is very important. So we said we have to separate your sidebands, no, upper sideband and lower sideband. So as to for generation of your SSB modulated signal, this is only possible when your message spectrum should be having an image energy gap at the origin. If it is not having, they both will be merged up. So this is very important, that we should be having an energy gap at the origin. Okay, for generation of your SSB modulated signal, it should be, if it is possible, we have to make it possible. Okay, so what we have to do, we have to have a energy gap at the center of the origin of your message spectrum. I hope you are clear with the steps of your generation of your SSB. I will repeat it. First you have to generate DSB signal, then you have to pass that DSB-SC signal to a band pass filter where it will be filtering out one of the sidebands. Okay, these two are the steps, and one of the important point that we should keep in note, that there should be energy gap at the origin of your message spectrum, so that you will get a SSB modulated wave. Clear? Okay. Next we will see how we are generating that one. So the most straightforward path to generate your SSB is first generate DSB-SC signal, then suppress one of the sideband by filtering. So this is your message signal M of t, and this is your which signal? This is your carrier signal cos 2 pi fct or omega ct. Okay, to these both are given to your modulator. This in combine gives you your DSB-SC signal where you are removing the carrier here itself. Then this is given to a sideband filter. This sideband, the only complexity here in this what we say SSB signal is the method should meet the filter requirements. Which filter actually we have to choose very wisely, that which filter we have to use for getting either lower sideband or upper sideband. This is the only one primary difficulty that you will be getting, means initial difficulty. सबसे पहला the initial difficulty that you are getting is to choose wisely which filter. If you want a USB upper sideband, mean higher frequency components, then you should use a low pass filter. If you are going for the lower sideband, you should use high pass filter to filter out the upper sidebands. Clear? So this is the first primary difficulty that you will be facing to choose which kind of filter you want to use. So this is how your block diagram is shown. Combination of your message signal and carrier signal, they both are given to your modulator, which gives rise to your DSB signal, double sideband suppressed carrier, and that is given to your sideband filter. Means sideband filter that removes one of the sideband. Okay, one of the sideband will be removed, and the signal which is obtained is called as your single sideband modulated signal. Now that was your frequency representation that we have seen in the first case, right? Now I'll show the time domain representation of your SSB modulated wave. So again we'll come from the initial, again and again. See, every topic what we have started in the analog communication with amplitude modulation, they all are related. First amplitude modulation, then DSB-SC, then SSB, then again you will be seeing VSB. So amplitude modulation, there you had a carrier, that carrier will be removed by using DSB-SC. Then you are having two sidebands, one of the sidebands will be reduced by using your SSB. So as to show this in the time domain representation, we are coming from the first initial step of your amplitude modulated wave. So what was the formula? Do you people remember? I hope. So what was the formula for the amplitude modulated wave? AC cos 2 pi fct. This is completely your carrier, plus your both the bands will be there. AC k m of t into cos 2 pi fct. We got these two sidebands in DSB-SC time domain representation that I have to give in the last class. I hope you people remember that one. In case if you don't, go back to the last previous video. Do check that one. Practice that all the equations. Then it will be very clear. If you are not going to practice, then it will be very difficult for your further steps. Clear? So DSB-SC, what we have done in double sideband, suppressed a carrier. This carrier is completely removed, and you are having only two bands, that is upper sideband and this is lower sideband. Now in SSB signal, as to generate this signal, we have to filter out one more band because it is taking more bandwidth. So as to reduce that one, I am removing either upper sideband or either lower sideband. So I am neglecting one of the lower sideband. What I will do, I will remove this one. Suppose either you can remove this or this. I am removing this lower sideband. Okay, so your SSB signal will be of AC AM by 2 into cos 2 pi FC plus FM into T, isn't it? So this is your only one sideband. So your sideband, upper sideband, can be given as by the formula. See, by what you can see by from here, cos of A plus B formula. Yes, are you getting it? So here you can replace this cos FC plus FM in terms of cos A plus B formula. What is cos A plus B formula? Cos A cos B minus sin A sin B. So you are neglecting one of the lower sideband. Then I am getting this part only upper sideband. This upper sideband can further multiply or further mathematically expressed in terms of cos A plus B formula. So what I am doing now, I am substituting this formula over in this equation. What I will get, the common term is amplitude of your carrier and amplitude of your message signal. I will take it as normal common. Then I will get cos 2 pi fct. This is A is nothing but your FC and B is your FM. These two are the variables. Okay, I am multiplying this cos 2 pi fct also. So cos 2 pi fct into cos 2 pi fmt, this is b, cos a cos b, minus sin a sin b. What is sin a? Sin 2 pi fct into sin 2 pi fmt. This is how you will be writing your equation. Further, if you multiply this ac am by 2, what you will get? ac am by 2 into cos 2 pi fct into cos 2 pi fmt minus ac am by 2 sin 2 pi fct into sin 2 pi fmt. This is how your single sideband modulation will be shown. Either it will be in upper sideband, either it will be of lower sideband. If I consider this lower sideband, neglecting of your upper sideband, then what I will get over here? I will get a plus mark. ac am by 2 cos 2 pi fct into cos 2 pi fmt plus, because minus into minus I will get a plus over here. Then again you will have ac am by 2 sin 2 pi fct into sin 2 pi fmt. I will show over here. This is how you will be taking. Now what I will do, I will substitute this am cos 2 pi fmt as m of t, okay, a variable message signal, and am sin 2 pi fmt as one of m cap of t variable. Now if I substitute these values, okay, cos 2 pi fct values, what I will get? A final answer of your single sideband modulated wave, that is SSB is equals to AC by 2, okay, m of t, that is am cos 2 pi fct into cos 2 pi fct plus or minus. Plus or minus, why we are saying we will get minus when you are having the upper sideband, we will get plus mark when you are having the lower sideband. Please do practice, you will get to know why we have written like this, okay. So if you are multiplying, I am substituting these values, then the final answer of your single sideband suppressive modulated wave is AC by 2, this is m of t into cos 2 pi fct plus or minus, then AC by 2, this is given as am sin 2 pi fct. I am substituting it as a variable m cap of t into sin 2 pi fct, okay. This is the time domain representation of your SSB modulated wave. If you are having the upper sideband, this is here, if only upper sideband is obtained, then what is the formula? AC by 2 m of t cos 2 pi fct minus AC by 2 m cap of t sin 2 pi fct. And again, if you are having the lower sideband is obtained, what is the formula? SLSB of t is equals to AC by 2 into m of t cos 2 pi fct plus, here you are seeing plus AC by 2 m cap of t sin 2 pi fct. So that's the reason the overall SSB signal I am given as single sideband modulated wave is given as AC by 2 m of t cos 2 pi fct plus or minus AC by 2 m cap of t sin 2 pi fct. I hope you are clear with the time domain representation of your single sideband modulated wave. Clear, ma? I hope everyone is clear. Okay, next we will see the spectrum of this one. What is actually the spectrum you are having? This is your message signal, complete frequency spectrum of your SSB signal, okay. So as we said, we are in DSBSC as well as in your amplitude modulated wave, what is the bandwidth? Twice that of your message signal or the modulated signal. Here as we are suppressing one of the band, one of the sidebands we are suppressing, so your bandwidth will also be decreased. So now the bandwidth of your SSB signal will be becomes omega. Instead of 2 FM or 2 omega, we are getting only omega, means your bandwidth is also decreased, isn't it or not? So sorry. So here you can see the message spectrum. The inner part of your message spectrum is always called as lower sidebands, and these are your upper sidebands. In case if you are applying a low pass filter over there, then you are getting the upper sidebands. This is how they will be transmitted. In case if you are going for the lower sideband, these are the things that you will be obtaining. Correct? So this is the overall spectrum of your SSB signal, how it will be obtained with your bandwidth, that is only omega. I hope you are clear with this one. Yes or not? So shall I repeat it once again? So what actually SSB system does, it reduces the, so when your one of the sideband is completely compressed, So what happens, the power of this also reduced. So this system, what it do, it reduce the transmission power by suppressing the carrier and also reducing the bandwidth and by suppressing one sideband. See, in only by using one single sideband we are having three advantages. See, one is the transmission power is suppressed, second your carrier is also suppressed, and transmission bandwidth is also reduced because we are suppressing one of the sidebands. So three things are done by using your single sideband. So this is more advantages. So one more advantages than this one is also there, that we will see in the next class. Okay, so this single sideband modulation is mainly used at your television, okay, telemetry or military communication, or in the radio navigation, where we require less bandwidth and less power consumption with a suppressed carrier. So these all are applications where you will be using, especially in your mobile systems we will be using this one. And TV also in telecom, because you will getting a video, audio both at a time we will be getting. So at this also we will be using your single sideband modulation techniques. Okay, clear? Next, now the power relation of your SSB-SC. What is the power relation? Do you remember in DSB-SC? What was the power relation in DSB-SC? The total, first I'll go with the power relation with your amplitude modulation. What total power of amplitude modulation PT was is equals to, you people remember, carrier power PC plus your, what was the power, carrier power of your sidebands, means your upper sidebands or lower sidebands. Now, okay, so what we have done in your DSB-SC, we have removed the carrier. So total power PT was is equals to your power of your upper sideband plus power of your lower sideband. Now what we are doing, we are reducing one of the sideband also now. So what will be your total power? If the carrier and one sideband is suppressed, then the total transmitted power is equals to one of the power of your sideband. So I will give it as power of SSB, means your suppressed sideband modulation, is equals to either power of your lower sideband or either the power of your upper sideband, and that is given as your mu square AC square by 8R. That this we have calculated in the last class itself, so that's why I have given it directly, but I am going to give you assignment for this also. Monday you people have to show that one. Okay, so your power of your SSB signal is equals to mu square AC square by 8R. This is the power of your power relation, or the power of your which one? That is your single sideband modulation. So this single sideband modulation can also be given as your PSSB is equals to mu square by 4 into PC. This is a, yes, we can write it or not, because what is the carrier power? AC square by 2R. This we have already discussed. How we will get this power? V square by R. This R is given as 2R here. Okay, so this PC is equals to AC square by 2R. So I am substituting this power of your SSB signal is equals to mu square by 4 into PC, whereas the power of your DSB-SC signal is equals to mu square by 2 into PC. So this is the assignment. I will post in the group also. You have to find out the percentage of power saving in your DSB-SC as well as your SSB signal. Okay. So this is the power of your SSB. What is the power of the SSB? Mu square by 4 into PC. Power of DSB-SC, remember that I am repeating it. Mu square by 2 into PC. This is mu square by 4 into PC. Okay. Now this is the percentage of power saving. Means by using your SSB signal, how much percentage of power is saved? This you have to calculate. How we have to calculate? What is the formula for that one? Power of DSB signal, means why we are considering this DSB signal, because first the main thing what we are considering is your DSB. First generation is on generation of your SSB is completely dependent on your DSB-SC. Means the what is it? The main base of your SSB is your DSB-SC. So the total power what we are considering is from your DSB-SC. So the total power power of DSB-SC minus power of SSB divided by DSB-SC. This is the assignment for you people. You have to calculate and tell me the percentage, how much percentage of power is saved by using your SSB. I have given the formulas, just you have to substitute and calculate. What is the formula for DSBSC? PC of 1 plus mu square by 2 is the power of your DSB-SC, double sideband modulated wave. And what is the power of your SSB? P SSB is equals to mu square by 4 into PC. This both you have to substitute in your power saving formula and you have to get what is the answer. I hope you people will do this, hopefully. Okay, now we'll go. Means how you have to formula, you have to find the efficiency, like mu is equals to 1 you have to substitute and mu is equals to 0.5 you substitute and tell me what is the how much percentage of power is saved for mu is equals to 1 and mu is equal to 0.5. okay, next we'll see what are the advantages and disadvantages of your SSB. As said, the very first advantage is your less power consumption. Why we are saying less power consumption? Because your carrier is totally suppressed, yes, or considerably it is reduced. Okay, then what you are having, one of the sideband is also reduced, then of course there will be less power consumption and much less total transmitted power which is used. Okay, if there is necessity of 100%, if you are having the power, then half of the power only is much more enough for your what SSBSC. So that's the reason we are saying that it is having less power consumption. And second one is conservation of your bandwidth. Of course your bandwidth is reduced. So in single sideband transmission or SSB transmission requires half as much of bandwidth compared to your of amplitude modulated wave or DSBSC FC wave. Yes or no? You used to have 2W or 2 omega, right? The bandwidth was 2 omega. Now the bandwidth is reduced to omega, means it is half of your DSB-FC signal or amplitude modulated wave. So we say that single sideband transmission requires only half as much of the bandwidth compared to that of your amplitude modulated wave, because you are eliminating one of the sideband which reduces the bandwidth by more than the factor of your half, by more than the half. So that's the reason we are saying that we are having conservation of bandwidth. Third one is noise reduction. How you say noise reduction? Okay, if it is your noise power has been reduced to half, okay, than that of your amplitude modulation wave. So both the bandwidth reduction and as well as your what you'll say immunity of the system is increased. So what happens here in this amplitude modulation, the noise will be reducing. Okay, the bandwidth has been reduced, but if you had 2 omega, you had only omega, means there is very less what we'll say chance of getting the noise in that particular bandwidth. Okay, we are only having first carrier wave was there, we are having much more chances of getting the noise very large in that one because of carrier wave. We have compressed the carrier wave, means considerably reduced. Okay, more like of समझ लीजिए कि उसको reduce ही कर दिया पूरा. Okay, considerably it has been reduced. Second one what we had here, one is carrier is suppressed and you have one of the sideband is also suppressed. So bandwidth has become half of it. So there is very narrow bandwidth. So there is no chance of getting the noise in that particular bandwidth. So mostly the noise will be reduced in your SSB. Okay. And the fourth one is reduction in carrier interface. So this is important because whenever we are having a larger carrier, there will be an interface. Interface is nothing but combining of other signals or other frequencies. So by using in this one, there is no carrier is transmitted, so there is no possibility of getting any interference of your carrier. So there is reduction in carrier interface. So that is what the 4 advantages. That is less power consumption. Okay, the power is also being consumed very less. Bandwidth is reduced to half. Noise is also reduced because of your bandwidth, and because we are suppressing the carrier, there is no interface of your carrier also. Okay, but we are having again 2 disadvantages. First disadvantage is your complex receivers. Again, see 2 disadvantages were there in your DSBSC. One was your
two identical sidebands were used to go, and due to that one more bandwidth is required, more power. So we have reduced one of the band. But the second disadvantage was there about your typical or the complex receivers, right? That still that disadvantage we are having, that we'll see how we have to reduce in the next class. Okay, what are the complex receivers? Means there should be proper synchronization, that is in terms of phase and frequency of the carrier, because you are suppressing the carrier at the transmitter side. When we are receiving at the receiver, the local oscillator should generate same carrier which we used in your transmitter side in terms of noise, in terms of frequency and phase. So that is one complex receiver. And tuning difficulties. Tuning should be there. Okay, proper frequency should be matched for your transmitter and the receiver carrier. Okay, carrier frequency should be same. So these are the two difficulties or the two disadvantages that we are facing in your SSB signal. That can be also be reduced by using your vertical sideband modulation, VSB. That we'll see in the next class. But for today's class, it was all about your SSBSC. Do you remember what is SSBSC? Shall we revise once again quickly? What is your SSBSC signal? What is SSBSC? Single sideband suppressed carrier, single sideband modulation. What is single sideband modulation actually does? It is the modulated signal where there is no carrier component and only one sideband. It means it requires a bandwidth equal to, first that bandwidth, DSBSC was having a bandwidth equal to twice of your message signal. Here we are having half of your message signal. Okay, so not half, it is equal to your message signal. Okay, the carrier and one of the sidebands are suppressed and no information is lost. So the transmission bandwidth required in this case is equal to the message bandwidth. That is more than enough for your modulation. Yes or no? So whatever the bandwidth your message signal is having, that much of your bandwidth is enough for our sidebands. If you are using two sidebands, we require twice that of your message signal. We don't need, why we unnecessarily waste the bandwidth, right? So whatever the message signal you are having, that message signal's equal bandwidth is taken by your one of the sidebands. So that's the reason this is one of the advantage of your single sideband modulation. Okay, so your SSB system, what it does, it reduces the power transmission, it suppresses the carrier, and the reduction, your bandwidth is also reduced. Okay, this was the advantage of your single sideband suppressed carrier. Either depending upon your receiver part, you choose which sideband you require, either upper sideband or either lower sideband. But very important thing is there should be energy gap between your two sidebands at the origin. Okay, at the center of the origin, so that they can be separated. This is very important. And two steps to generate your SSB is, first to generate DSBSC, and that DSB signal should be given to one sideband filter. Okay, these are the generation part, and this is your time domain representation of your SSBSC. How you are going to show a time domain, and what is the loss formula for your SSBSC? AC by 2 m of t into cos 2 pi fct plus or minus, for both upper sideband and lower sideband, AC by 2 m cap of t into sine 2 pi fct. So this is your frequency spectrum of your overall, the spectrum of your upper sidebands and lower sidebands and your reconstructed SSB. Okay, these are the power formula. Because you are having same equal and identical power, identical information, the power is given as P SSB is equals to P LSB is equals to P USB. So mu square into AC square divided by 8R, and that is given as your mu square by 4 into PC, as carrier power is given as AC square by 2R. Okay, and this is the percentage of power saving. This is the assignment for you people. You have to find out the percentage of power saving for DSBSC as well as SSB. For both the values, modulation index mu value should be given as 1 and 0.5. What is that? You have to give the assignment. I'll give a Google form. You attach your assignments in that through that Google form. Okay. So these are the advantages and disadvantages. I'll quickly revise once again the advantages. You have less power consumption, bandwidth is reduced to half, noise is mostly reduced, and reduction of carrier interference. Whatever the interference due to carrier, what you used to obtain in amplitude modulation, that is reduced. But there are two more disadvantages. Complex receivers, of course there will be difficulty when you have to get the carrier over there, and you should also see the tuning difficulties, because we have to tune, the frequency should be tuned. That are the difficulties that we will be facing, but this also can be reduced by using your vestigial sideband modulation. That we'll see in next class. I hope you are clear with the SSB-SC topic. In case of any doubts, please let me know. Okay, for today's class, we'll end the class up to here. Thank you.